So we're learning about our Laplace transforms, and every time we come to class, we sort of expand what we know. So we have sort of two categories. We have functions, and we have rules. And so the functions are, we have a base collection of functions that we say, look, these are things which we should be familiar with and we should be comfortable with. And more or less, we want to make sure we understand the various forms, how to quickly find them, and how to make sure we write things in the right way so that we can work with them. Now, the rules, this other side, is all about saying, okay, what are things we can do? So, for instance, what happens if we multiply by an exponential function? Well, that turns out to be a shift. Or what happens if we take derivatives, or if we multiply by t's? What about if the output is a product? What was the input like? So we have these collection of rules. Now, oftentimes, we don't explicitly state this out loud, so let's go ahead and just make it clear that even though we only write it in terms of the Laplace of this equals that, each rule actually has a second rule that goes along with it. So for instance, when we talk about convolution, we say, the Laplace transform of f star g is this f of s g of s. But really, this could also have been written as the Laplace inverse of f g. So in other words, I'm just taking the Laplace inverse of that is f star g. So make sure you're comfortable enough to say, hey, I understand every rule for Laplace. There's a corresponding rule for the inverse Laplace, and know how to work with them. Now today we're going to add just one new rule, which is great because it's a wonderful rule. And it's this rule that you see boxed here. And what does it say? Well, it says the Laplace transform of u of t minus a f of t minus a is e to the minus as f of s. And so we're going to get into that. What does that mean? How do we derive this rule? And really, how do we use this rule? Now, I've mentioned before, I love the wonderful symmetry that often shows up in these rules. And for this one, I like to think about this Laplace transform e to the ct f of t. It says here that if you multiply your input into the Laplace transform by an exponential function, the result is a shift. Well, what we're going to see is what's really happening here is that this is essentially a shift of your function. And what's the effect? Well, the effect is an exponential function being added onto the front. So there's this beautiful symmetry going on. All right, well, let's get right into it. So the very first thing we want to do today is find the following. The Laplace transform of u of t minus a f of t minus a. And I know what you're thinking. Aha, Steve, good news. It's right there. Well, we want to see why it's right there. Okay, so that's our goal. Now, before we get going, I do want to sort of get the picture of what this is saying here. All right, so what's going on? We have our normal graph. Let's say that we'll graph here f of t. And if you recall, when we talk about Laplace transforms, we only care what happens starting at time 0. Okay, so I don't care what happens before 0. So f of t does something. So, okay, it does that. Let's just say that's f of t. Now, let's talk about our pieces. We have u of t minus a, f of t minus a. Now, this u of t minus a, what is that going to do? What does this function do? It's like an on-off switch. So u stands for a unit step function. And it says, look, if I'm negative for the input of u, I'm 0. If I'm positive for the input of u, I'm 1. And so when I see this u of t minus a, it's really saying, look, everything is turned off until a. So before a, I'm 0. Nothing's happened. Now, after a, I'm turned on. My function is in the on position. So then I say, okay, after a, this part is 1, I have f of t minus a. Well, what's the relationship between f of t and f of t minus a? It's a shift. In which direction? To the right. So it's the same picture. Now I regret drawing so many wiggles. Wiggle, wiggle, wiggle. Okay, so it's the same thing that's just been shifted over to the right. So when we see this expression, it's really saying, hey, what happens when we shift things over? So that's the idea. So that's what we're trying to understand. What happens when we shift things over? All right, well, when we have to find a formula, we don't have anything yet, where do we start? We start with the definition. So, we have the Laplace transform. U t minus a, f of t minus a is integral 0 to infinity e to the minus st times the function u t minus a, f t minus a, and dt. All right, that's what we have. Okay, well, this u of t minus a, what does that tell us about our integral? Change the bounds. Okay, where are we changing the bounds to? A to infinity. Why do we change our bounds from a to infinity? Yeah, so the key here, this will be 0 for t below a. So it says, look, if you're below a, you're getting 0 out. So that's sort of unimportant because it's not important. So we can say, hey, we can rewrite this as the integral a to infinity. In other words, remove the part where I'm in the off mode. And then we have e to the minus st. And now, since I'm starting at a, I'm in the on mode. So I can rewrite that, f of t minus a. All right. Well, that wasn't so bad. But now we look at this and say, what can we do? Well, we'd like this to look like a Laplace transform. We'd like to get our bound back to 0. So what do? The other thing, of course, we'd like the inside to not be t minus a. We'd just like it to be t or whatever your favorite variable name is. So an idea, substitution. Let's call this part u. So u equals t minus a. So remember here, a is a constant. What is du? dt. All right, well that's good. All right, so u equals t minus a. Another way to say this is that t is equal to u plus a. True story. Just move the a across. Now remember, every time we make a substitution, we've got to update everything where t was involved. Okay, so this is going to become our integral e to the minus s. Now t becomes u plus a. Our f of t minus a becomes f of u. Our dt becomes du. What else do we need to do? Bounds. Now remember, these bounds are t bounds. T equals a to t equals infinity. And we want to go to the point where we have our u bounds. u equals something to u equals something. And to figure it out, we say, okay, if t equals a, what does u equal? 0. As t goes to infinity, what does u do? Also goes to infinity. So that our bounds are 0 to infinity. And now we're like, oh, this is nice. Clean it up a little bit. What can we do? Well, we can say that this is integral 0 to infinity e to the minus s times u. So I'm just, and then, and if you think about what's happening, we have e to the minus su minus sa upstairs, but because of exponentials, you can actually pull that apart. And then we have our f of u du. Okay, we're almost there. Now, this piece, e to the minus s times a, or e to the minus a times s, whichever way you like to write it, with respect to this integral, what is it? It's a constant. Our integral asks about u. There's no u. Since it's a constant, where can we put it? We can put it outside the integral. So we'll move it out, and well, we'll rewrite it as, instead of s times a times s. So e to the minus a times s, integral 0 to infinity, e to the minus s times u, f of u du. And now we're like, what? That looks familiar. What is that? It's the Laplace transform of f. Yeah, the thing is, this u is just a dummy variable. We can replace it whatever we want. So this is the same thing as capital F of s. Which, if you go back, is what we were claiming. E to the minus as capital F of s. All right, so good. Now we know. Now we know. And as the saying goes, knowing is half the battle. All right. Well, I guess we have to do the other half. Doing, right? Okay, so what's the moral here? Well, the moral here is we're going to practice doing this. The key is when we're doing it the forward direction, in other words, we want to take the Laplace transform of something, if we ever see a u attached to our expression, u of t minus something, we say, okay, we need to make sure we rewrite our function as f of t minus something. So we have to, if I see a u of t minus 2, I say I have to rewrite my function in terms of t minus 2. If I see a t minus 3, it has to be written as terms of t minus 3. And then it'll be pretty straightforward. There is, of course, the other direction, which remember, every rule comes in pairs. So whenever we take the Laplace inverse, e to the minus as capital F of s, we say, aha, whenever we see this in our inverse Laplace, that means a shift happened. And so we have our u of t minus a, and then our function will also have had a shift, f of t minus a. So we want to make sure we're comfortable using both ways. So we're going to practice going in both directions. So let's start with forward direction. All right. Example. Find the Laplace transforms of the following. Oh, we're going to get lots of practice here. E to the 2 minus t times u of t minus 2. So we'll start with that one. Now, we see a t minus 2 because it's there. That says I want to rewrite the function part in terms of t minus 2. So is there an easy way for me to rewrite e to the 2 minus t as something involving t minus 2? Yeah, so we say, aha, this is e to the minus t minus 2, u of t minus 2. All right, now we're ready to take the Laplace transform. So what's going to happen, we see that the Laplace transform of this expression, well, we see our u of t minus 2. That says there's a shift. So we're going to have e to the minus 2s. Now, what's our function? It's not e to the minus 2 minus 2. It's our function we're cluing off of is the unshifted function. So our unshifted function is what function? E to the minus t. What does e minus t go to? Well, we look up on our chart. E to the minus t will go to 1 over s minus minus 1, also known as 1 over s plus 1. And we're done. All right. Are we good? We got it? Yes? Okay. Next problem. There's a whole bunch of them. We're going to get really good. Cosine 2t, u of t minus pi. All right. Are we ready to go with our Laplace transform yet? No. Because we need to rewrite this function in terms of t minus pi. And you're like, okay, cool. Let's do it. How do we do it? Well, that's cosine of 2. Now here's the really amazing fact. It turns out that t is the same as t minus pi plus pi. It's absolutely true. I just subtract, I add, life is good. Now, why do we do that? Well, because I want to get a t minus pi in there. Okay, so this is the same as cosine of 2 times t minus pi plus 2 pi, u of t minus pi. All right, now let's use some knowledge of trig. When I add 2 pi on the inside of my trig function, what happens? It shifts it over by 2 pi. So what does this become? What's the effect of shifting your trig function by 2 pi? It's the same thing, because trig functions are periodic. So we say, aha, this is actually cosine of 2 t minus pi, u of t minus pi. And now you're like, well, gosh, Steve, that was a lot of work to just put a minus pi in there, but, well, we've got to do it. And why do we have to do it? Because, again, our goal, we want this piece to match that piece. Because in order to use the rule, things have to match. All right. So we now do the Laplace transform of this. Cosine 2 t minus pi, u of t minus pi. We see that u of t minus pi, that says we're going to have e to the minus pi s. And when we look at the first function, we say, what are we cluing off of? Well, we're not going to clue off of the cosine 2 times t minus pi. We're going to clue off of just cosine 2t. So we come to our chart and say, okay, cosine 2t would be what? Well, cosine of bt is s over s squared plus b squared. So cosine 2t, s over s squared plus 4. So far, so good? All right. Moving down our list. Sine of t times u of t minus pi halves. This should be fun. Okay. Well, are we ready to do our Laplace transform? Yes? No? No? Well, we're not, right? Because the insides don't match. So we got to make this look like a minus pi halves. Okay, so we do the same thing. When in doubt, just apply it, right? So this is sine of t minus pi halves plus pi halves u t minus pi halves. All right. Let's test your trig knowledge. If I add pi halves to the inside of the sine function, what do I have? What is it? It's cosine. This is cosine of t minus pi halves u of t minus pi halves. Using knowledge of trig. Trig, what a wonderful, wonderful time. Okay, so we now have rewritten it so that the insides match. Life is good. All right, so what do we have? Well, it says the Laplace transform, cosine t minus pi halves, u of t minus pi halves will be, well, what's in the exponential function?
Negative pi halves s.
U negative pi halves s. Okay, and then we come to our piece here. We're cluing off of the cosine function. We say, well, what does cosine look like? And that is s over s squared plus 1 squared. All right. Well, 3 down, 2 to go. All right. Next one. T, if we're between 0 and 1, 2 minus t if we're from 1 to 2, and 0 otherwise. All right, so this is a piecewise function. And so whenever we have piecewise functions, we should expect to see the function u. Because u is built for handling piecewise things. So how does it work? Well, so the basic idea is you do the following. If you change behavior at t equals a, sorry, this takes a second to write down, what you're going to have is you're going to have a on-off switch at a, so that's your u of t minus a. And then you say, you take the behavior after a, and you subtract your behavior before a. Now you might say, I'm having a very deja vu moment. This sounds like something I've heard before, because it is. We talked about this last week, I believe. So the key here is to think about, when I'm doing an on-off switch, this plus part is being turned on, and this minus part is what's being turned off. So you're turning on what should be happening, you turn off what was happening. All right, so this function, let's rewrite it using our unit step functions. What's our initial behavior?
0.
It's t, because we care where we start. So our initial behavior is t, because we only care about what happens above 0. All right, where is our first switch going to happen? At 1. Okay, so we're going to have u of t minus 1. All right. What do we put? Well, what's the behavior after 1? It's 2 minus t. What's the behavior before 1? It's t. So u, t minus 1, 2 minus t, subtract t. All right, where's our next switch occur? Two. So if u of t minus 2, What's happening after 2? 0. What's happening before 2? 2 minus t. Okay, so our piecewise function can be rewritten in this format. All right, well, let's rewrite this yet again. So 2 minus t, that's 2 minus 2t. And here, 0 minus 2 minus t is the same as t minus 2. Now our goal is to make sure that whatever I'm attaching to has the right form. So I see a t minus 1. That says I want to write this in terms of t minus 1. How can I rewrite 2 minus 2t in terms of t minus 1? Pull out a minus 2. So this is minus 2, t minus 1. So we have t minus 2, t minus 1, u of t minus 1, plus t minus 2, u of t minus 2. All right, are we ready to take Laplace transforms? Yes, everything's in the right form. Okay, so we have the Laplace transform of t minus 2, Laplace transform t minus 1, u of t minus 1, and plus the Laplace transform t minus 2, u of t minus 2. Okay, well, what is the Laplace transform of t? Do we know that? Laplace transform of t is 1 over s squared. Okay, subtract 2. Because of the u of t minus 1, what do we need to put? E to the negative s. And what do we multiply by? 1 over s squared. Because this t minus 1 is really just the function t that's been shifted. So 1 over s squared. Then we come plus, here u of t minus 2, so we have e to minus 2s. And now, what do we multiply that by? 1 over s squared again, because it's the same function. It's still t, it's just been shifted over. And so that's actually a perfectly fine answer. We can, if we wanted to, pull out a 1 over s squared and 1 minus 2e to the minus s plus e to the minus 2s. And there we go. On a side note, that's 1 minus e to the minus s squared. Oh, okay. All right, cool. All right. One more? Yes? All right. Once more. Okay. So, unfortunately, I ran out of space, but that's all right. We have copy technology. T squared, u of t minus 1, u of 3 minus t. All right. We want to take the Laplace transform of that. What do we need to do? Okay. Simplify how? Rewrite. Yes, that's a good strategy. How? All right. Let's talk about this latter part. U t minus 1, u of 3 minus t. You have a series of on-offs connected together. And the interesting points are 1 and 3, because those are when you're flipping a switch, one way or the other. What happens before 1? Are we on or off? Off. Because if I plug in like 0, u of negative 1 is in the off position, u of 3 is in the on position, but off times on, 0 times 1 is 0. So I'm off. What if I'm above 3? Like 100 or 4. I'll be off again. 3 subtract 4 is negative. So this second part is off. And if either part is off, the whole thing's off. What about between 1 and 3? Then we're on. Because 2 minus 1 is positive, 3 minus 2 is positive. So we're on. So what's going on? Well, it's basically saying that this function here is the function that is the t squared, so it's just doing this, between 1 and 3. But otherwise it's 0. So it's 0, it looks like t squared, it's 0. So this is our function. And we're trying to take the Laplace transform on. All right, well, so embracing the philosophy we just talked about, say, okay, we change behavior at 1. So we're going to have a u t minus 1. And what do we multiply that by? So the behavior afterward is t squared. Behavior before is 0. So we can say initially our behavior is 0 plus, okay. And now we have something happening at t minus 3. Okay, what's our behavior after 3? 0. Subtract behavior before 3, t squared. All right, so our real goal here is we have, right, it says t squared u of t minus 1 minus t squared u of t minus 3. Okay, so that's our function in a more friendly, digestible way, and at least friendly in terms of our rules. Okay, what do we do? Are we ready to apply our rules?
Yes.
No, we're not ready yet. What's our issue? For the first part, we need to write t squared in terms of t minus 1. Right now it's in terms of t. So what do we do? What do we do? Well, t squared is also the same as t minus 1 plus 1 squared. So u of t minus 1. And over here, t squared, in this case, we need t minus 3. So t minus 3 plus 3 squared. Okay, so t minus 1 plus 1 quantity squared. What's another way to write that? T minus 1 squared plus 2 times t minus 1 plus 1. We expand, FOIL it out. Think of this as like a plus b. A squared, 2ab, b squared. Over here, we're going to get t minus 3 squared plus 6 t minus 3 plus 9 u of t minus 3. Now are we ready? Yes. Okay. So we see the u of t minus 1. We know that that's going to become e to the minus s. And now we just think of our individual pieces. 1 goes to 1 over s. This is our 2t that's been shifted. So that would be 2 times 1 over s squared. And t minus 1 squared, well, if we come here, t squared goes to 2 factorial over s cubed. So this will go to 2 factorial over s cubed. Minus, all right, the u of t minus 3 goes e to the minus 3s. The 9, what will that go to? 9 over s. You can think of it as 9 times 1 over s. The 6t minus 3, what does that happen to become? 6 times 1 over s squared. And the t minus 3 squared becomes 2 factorial over s cubed. And there's our answer. Probably a lot bigger than you expected. Because you look at the initial thing and like, oh, that seems pretty compact. And you're like, oh. That's a little bit longer. All right. How are you doing? Hanging in there? Yes?
Can I ask why are we able to flip like the u minus t goes to u t minus t? Can you explain why?
Well, sure. Because it didn't do that. You're thinking it did that. Because you're connecting the beginning and the end. But you shouldn't try to connect the beginning and the end. What was happening is rather, you should think of it in this way. U of t minus 1, u of 3 minus t. We said, oh, that says our picture looks like the following, where off 1, on 1 to 3, off again. And then we said, oh, come from the picture, which is really just a way of saying understanding the function, saying, hey, this says you turn on at t minus 1, you turn off at 3. So it's not that we went from here to there, it's rather we went from here to understanding to new expression. So that's how I recommend you do it.
In the case where we have two u's or multiple, would two offs make an on, or would it be off with two zeros?
Yeah, so this is not the case of two wrongs make a right. Yeah, so two, if anything is off, and you're multiplying, the whole thing's off. Do we have an answer? The inverse Laplace of e to the minus 3s times s cubed. Someone said a half? Okay, 1/2 u t minus 3. Because we see the e to the minus 3s, we know there's going to be a u of t minus 3. What else do we need? And t minus 3 squared. Right? Because this, normally s cubed, if we just saw that, would be 1/2 t squared. But we've shifted, and so we have to make sure we carry out the shift. Okay, how about this one? Now, we can rewrite this, by the way, as e to the minus pi s times something over s squared plus 4. Well, what do we really want upstairs on top of s squared plus 4? A 2. Well, okay, so throw in a half somewhere. Okay, so what do we have? Well, the half will be a half. U of t minus pi and sine of 2, because this is a 2 squared, 2 t minus pi. Now, could you rewrite that? Well, yeah. Anytime there's a trig function, the moral of the story is I can rewrite it. 2t minus 2 pi, what happens when you do 2 pi on the inside? It doesn't matter, because it's 2 pi periodic. So you could rewrite that as sine of 2t. All right. How'd you do? Got that? Good? Okay. Should we do some more? How about we tackle this bottom one? E to the minus s over s minus 1 minus e to the 2 minus 2s over s minus 1. Well, what are some things we can do here? Pull it apart. I like that. Now, of course, when we pull things apart, we can only pull it apart using the upstairs. That are partial fractions. So e to the minus s, s minus 1. Subtract e to the 2 minus 2s over s minus 1. Now, how do we handle this e to the 2 minus 2s? So if you just had e to the 2s minus 2s, like, all right, life is good, I can do that. But there's that e to the 2 minus 2s. Well, we can use properties of exponentials. So whenever we have addition or subtraction upstairs, becomes multiplication. And that e squared, how do we treat it? A constant. Why do we treat it like a constant? Because it's a constant. Yeah, that's a good reason to treat it like a constant. Okay. So when we think about this inverse Laplace, we'll have e to the minus s, 1 over s minus 1, and then subtract e squared, e to the minus 2s, 1 over s minus 1. Okay, now normally 1 over s minus 1, what would that go to? Just this piece, what would that go to? Now normally this would go to the e to the t. Here we see e to the minus s, so this is going to be a shift by 1. So when we put these two together, what do we end up with? So it'll be e to the t minus 1 and u of t minus 1. Okay, so e squared, well, that just goes to e squared. E to the minus 2s, that tells us a shift by 2. 1 over s minus 1 says, well, normally you go to e to the t. So when we put this all together, well, we have e squared, and then what else do we have? U of t minus 2, e to the t minus 2. Now, can we clean anything up? What happens when we combine those? The 2 and the minus 2 cancel out. So this can also be written as u of t minus 1, e to the t minus 1, and then minus u of t minus 2 times e to the t. All right. Well, a minute left. Should we try to tackle this last one? Yeah. Let's do it. Let's do it. All right. So if we're going to tackle this last one, well, what do we need? More space. But what should we do here? Yeah, pull it apart. So this is s over s squared plus pi squared and plus e to the minus 3s s squared plus pi squared. Now this is fine as is, but here what would we want to do? Yeah, throw a pi upstairs because that will help us fit our mold. So the s over s squared plus pi squared becomes cosine pi t plus the 1 over pi. Now here we see e to the minus 3s, so we're going to have a shift by 3. And normally pi over s squared plus pi squared does what? Sine pi t. But now because of our shift by 3, it becomes sine of pi times t minus 3. You can leave your answer like this. If you wanted to, you could even multiply it out. If you did sine, let's just make one last thing here. Sine of pi t minus 3 pi, How does that relate to sine? Yeah, it's negative sine. Now for everyone like, oh my gosh, do I need to know all these things about trig functions? No. No. But isn't it fun? Walk down memory lane.